Amongst the electronic devices, there's a field called digital electronics, which only deals with two states, on and off. And they rely on what we know as the binary number system. The binary number system relies on just two digits, 0 and 1, to perform all the math and computation. Now, they use all these numbers can be represented with just on-off states in a switch. And whatever arithmetic we can do in a normal numbers that we use, the decimal number system, can also be done using the binary number system. And we can use mechanisms to convert these binary numbers to the number system that we understand. And that's how computers evolved significantly with this particular innovation of digital computers, right? So today we all our mainstream computers are digital. One of you asked me, what's inside a hard drive? Here's a hard drive I have. And yeah, I'll show you what this is. Actually, I took it out from the hard drive. I opened up all the screws, so it'll save time. So if you take up any hard disk, this is a very old hard disk. That's why it looks very big, bulky, right? Today's hard drives, especially the ones that you find in the laptop, are very slim, lightweight. But if it's a electromechanical hard drive, which will look like this at the back, there's a motor here. There's a motor. This is called a spindle motor. You'll see the inside of it. And there's a control board circuitry, right? These are electromechanical hard drives, and they actually store data by magnetizing things inside it. This is an opened up hard drive, which you see here. I just opened up the cover, and what you see here looks like a mirror, right? Mirror. You can actually see my camera, my ceiling, and everything. Oh, yeah, my phone, which is taking the actual shot. This mirror surface that you see is nothing but it used to be, right? These days it is glass. In early days, they used to have a strong metal and plate it with magnetic coating, but now it's all glass. On glass, they're given a magnetic coating, just like a real mirror. But then this magnetic coating is used to magnetize. And this arm that you see, this is called as a head, right? This is a head. And yeah, this head is actually right now blocked. This head is in what we call a sparking position, which means when you're moving the hard drive, you don't want the head to just wiggle around and scratch the surface. So they keep it in park position. The moment you power up your hard drive, there's a small actuator arm that moves around here. See this? There's a small magnet, which actually gets repelled when you apply current to a coil below it, and it just moves, making this head move freely now. And this head is actually connected to a coil that you see here. It's a small coil of wires. It's a very thin coil. And beneath this is a strong magnet, a very strong magnet. Actually, I opened it up. In reality, the hard disk would have this closed. There's another magnet here. This closes on top. Oh my God, this is very strong. The moment my fingers slip inside, it'll hurt my finger. This is a very strong magnet that you see. This one, this surface is a magnet surface. In fact, beneath this, you have a motor like this. This is a spindle motor. When powered on, you can rotate this motor almost to 7,200 rotations per minute. It's very fast. Generally, they start from 5,400 to 7,200. There are some of them that even go to 8,400 RPM. They rotate very fast. And while this is rotating, this particular arm moves. This arm moves, right? Actually, rapidly oscillates. It oscillates very rapidly, back and forth, back and forth, back and forth. It oscillates, and you'll store data in all these areas here. That's how data is being stored while it is rotating, right? So this is a technology that is there, and all this controlling of how much this must move, when this would store data, retrieve data, are all done by this control board, which is there here, right? That takes care of most of these activities. Oh yeah. This laptop is gone. Okay, so you can see the laptop. I just opened it apart. There was a keyboard over here. I think I have that also here. This is a keyboard, by the way. Only few keys are there. Okay, sorry, it's taking the screenshot. Hang on a minute. Yeah, there's a keyboard that was there. I removed all the keys just to see if I could find any screws. Couldn't find any screws here. This just came out, and there's a control board. And when you see what's inside it, you find a lot of stuff. Okay, you'll find some control board for the touchpad. I'll just move. I should show it across. The most important part is this one. This is a laptop's motherboard. What do you see here? The brain of the laptop, the motherboard, right? And this motherboard, in fact, you can see the silicon here. This is a silicon. This is a silicon material, shiny silicon mirror, right? This and this. Guess what this is? The CPU, the microprocessor. This is the brain of this motherboard, right? Maybe you could, in a brain, you have different components, right? The cerebellum, and all that. All the processing is done in this chip. And this silicon die that you see has a circuit, which you can't see in your naked eye. It's like they etch the circuit like in a film. It's a microscopic in size with billions of switches. Billions of components are there in it. You might ask me, what's this close cousin here? Looking a little smaller. This is a graphics processing unit, GPU. Today's computers are filled with graphics, right? All of these, the graphical user interface that you see. For driving all the graphics, the CPU alone is not sufficient. You need another chip which is almost as capable as CPU, called a GPU. On this motherboard, the GPU is small, the CPU is big. If you buy a gaming laptop or if you have a gaming computer, it's the opposite. The GPU is very big. In fact, the GPU comes in a card with all the fans and heat sink and so on, because they generate a lot of heat, because they have a very big silicon base with a lot of very complex circuitry there. They run to trillions of transistors. Yes. This is actually RAM, random access memory. This is the RAM module that goes inside this slot here. Because it's a laptop, the RAM comes in this particular format. But if you're building a real PC, a desktop computer, if you have a desktop, the RAM could be slightly more bigger if it's replaceable. But I'll tell you what, today's computers and today's laptops, you don't have an option to have these separately. They're all soldered. They're all on the motherboard directly. You cannot replace them. There's an old computer where you can actually take this RAM out and put a new RAM module to upgrade the RAM. For example, this RAM is just 1 gigabyte, 1 GB. But then I want to increase the RAM from 1 GB to, let's say, 4 gigabyte. I could just swap it out and buy a 4 GB module, place it in this particular location. But today's computers, as they become more and more sleeker, it's becoming more expensive to create all these slots and all that. So they put it all on the motherboard, like chips like these. If you're having a MacBook and so on, I don't think you have an option to replace RAM. Okay. So if at all you have the outermost electron that's free to move, not bonded to the atoms very strongly, the current atom or the neighboring atom, right? These materials where the electrons freely move are called conductors. These are called as electrical conductors, to be more specific. There are heat conductors that conduct heat. There are electrical conductors that conduct electricity. They allow flow of electrons freely across the entire material. And most metals I've seen, almost all of them, are conductors. For example, if you take any of the metals, any metal for that matter is a conductor. I have a small circuitry to show that. I will tell you how to create this. There's a continuity tester. You can use this to find out whether something is a conductor. I have a pencil here. I have sharpened both ends of this pencil. To know whether it's a conductor or not, you can just put one side of this pin here, and the other side, if it's a conductor, you can see it gives a beep sound and a very mild beep sound, and you can see the LED glowing, right? The light glowing there. So this is a conductor. And you do have some of these, like I have this plastic here. It's a transparent plastic. It's actually an acrylic material. Will it conduct electricity? Let's see. I just add this in here and add the pin here. It's not glowing, right? It's not glowing. The air, there's air between this pin and this pin, right? That also doesn't conduct electricity. These are called as insulators, right? These are called as insulators. What are insulators? They don't allow free flow of electrons across them. Whereas conductors allow flow of electrons. Therefore, you can have electricity flowing from one part of your power source to the other part. Now, if you take any electrical circuit, they essentially contain two components. Where was it? Yeah, this one. Yeah. The two parts. You would have a power source. Here I have a battery. You can have batteries in different shapes and sizes. I'll talk about more about it. Next class, I will continue. I'll talk more about it. This is a lithium battery. It's a lithium ion battery, which is rechargeable, but you might find batteries that look like this, right? It's very commonly found in toys and some gadgets. This also is a battery. There are two pins here. And the most common one are these. I'm sure these cells you people should have definitely seen in toys, right? Yeah, Sheshanand asked a question. Is salt water a conductor? Yes. Only pure distilled water might not conduct electricity. I would not say it's a good insulator, but it insulates, right? But if you add a little bit of salt in it, or any kind of electrolyte, or even acid in it, or alkali in it, it becomes a conductor, right? So salt water, mild acids, if you use lemon juice in distilled water, or even if you put vinegar in distilled water, or if you put baking soda in distilled water, all of these are different kinds of electrolytes, we say. They make water conductors, right? Why are the pins of the battery in different shapes? It's basically standardization. There are different standards for a battery, right? This is called as a double A cell. It's called just two A's. They spelled with two A's, right? Two capital A's. And this cell would have a negative point in here, and there's a positive point. So what is negative? What is positive? This is a place where electrons are trying to escape. Where? This side. Electrons are trying to escape. If you have a wire connected, like in this case, in this one, right? In this one, electrons are trying to escape in this part because this is a negative side. This battery also, if you just rotate it and see it across, they'll tell you which is positive, which is negative. See, they put a positive sign here, and they put a negative sign here, right? This battery and this battery are different because the technology is different. This is your normal cell, but this is a lithium cell, which gives you a slightly higher power compared to this battery. That's why they have changed the way the technology is. They almost look similar. They have a positive side here and negative side here, and they connect, right? Different manufacturers come out with their own way of packaging. And this battery, this is negative, this is positive. It's written somewhere here. See, positive sign here, there's negative sign here. You can see that. Conductors allow flow of electrons. See, in this case, I have this battery here. I have connected this metal plate. Actually, it's a sticker. This is not very reliable. I realize it. You'll see a lot of loose contacts, but then you can see the negative side of this battery is connected through this. And there's a crocodile clip to which I've connected an LED again through metal. That this particular light has two pins. The two pins are connected behind. You might be able to see it here. There are two pins connected to the side. And there's another connection here, right? I'm not sure why this turned on. Hang on a minute. Okay. Yeah. And you can see this. Now, this circuit is an open circuit. This is an open circuit. Yeah, it's an aluminum foil. Aluminum foil is a conductor. Why? Because aluminum is a metal. All metals conduct electricity. Almost all of them that you see, that you normally use, will conduct electricity, be it aluminum, stainless steel. I showed you right here. Remember, I showed you this continuity tester? Where was that? Okay. Yeah, here it is. See this. This is a continuity tester. It conducts. See this? It conducts. Paper, it does not conduct. See this. All of these are metal. All of these are metal areas. They conduct electricity. Almost all metals conduct them. Even this, when this is metal, right? See, anything that's shiny like this looks like a metal, isn't it? Yeah, you just see, it conducts. You can see a light glowing, right? If you look at all these things like plastic, I think this is some kind of a fake leather, fox leather. It doesn't conduct because obviously this is an insulator, right? Plastic, glass, all of these are insulators. All kinds of, most of the plastics that you see normally, they're all insulators. Glass is an insulator, ceramic is an insulator. What about rock and stone? They're all insulators. Again, it depends. There are some rocks which might have metal deposits that can conduct, but normally if you take a granite rock, a granite slab that we normally use at home, they don't conduct electricity, right? But yes, wet surfaces will conduct electricity because of salt water. The drinking water that we use, that we drink, that also has got a little bit of salt, and that is enough to conduct electricity. So if you make this entire thing wet, that will also conduct electricity. What about wood? Dry wood is an insulator. Wood does not conduct electricity. But if your wood is wet, sufficiently wet, it can conduct electricity. Should be careful. So is foam. Foam and rubber, if it's wet, if you soak it in water and all, then it might conduct electricity. But if it's dry, it does not conduct electricity. Is gold a good conductor? Okay, gold is a conductor. Yes, gold also is a conductor of electricity. You know what? All of these are literally gold. You see this? These platings? They look like gold, isn't it? They don't look like gold. They are gold. I'm not making this up. This is a gold plating. They put a very thin plating of gold. You know, there are people, there are like a couple of these people, what they do is that they have the shops where they take all these disposed motherboards, boards like these. And you know what they do with them? They process them and try to extract gold. But they have to get like 100 kilograms or 200 kilograms of material, like thousands of material like this, will get 1 gram of gold, perhaps. But still worth a try. People do that. So all of these are gold plating. You might ask me why they put gold plating here. Gold is a metal that is very inert. It's a very inert metal. What is an inert metal? It does not react, it does not corrode, does not oxidize. See, if you use this metal itself, let me show you. I create a circuit during the demonstration phase to show your parents what I'm going to be covering. I thought I'll use the same circuit, but I created some more, which I will show you next class. But what happened was, see, I tried to create a switch here. This used to turn on when moment I put this in here, but now it's not turning on. So it's flickering. Do you see that? The light is flickering. You know why it's flickering? There's a thin layer of oxidation that happened on this aluminum. This aluminum actually has a thin layer of oxidation. And this oxidation can create what we call as insulation and loose contacts, because it's actually acting as insulator here now. See, though these two are metals, when I touch it here, nothing happens. It's not conducting, right? It's not conducting. I have to put it on top, but I have to press it and scratch it like this, and then then the light sort of flickers. So yes, many of these metals might get an oxide layer, and once they get an oxide layer, they will not conduct electricity very well. And when you have this kind of flickering lights like this, it's called as a loose contact, a symptom of a loose contact. The contact is not tight, so the electricity is not flowing all the time. To avoid that, they actually try to make sure that all these circuits, right, when they're connectors, they plate them with gold plating. Most of them, they provide gold plating so that gold does not corrode, and therefore it will not lead to loose contacts. So yeah, if I had made this with gold, it has been intact, but you know, it's very expensive. Gold is very expensive. So think of a gate like we see in real world, right? So in real world, we use gates to enter into our house and so on, right? So I could create a nice model and show you, but you know, I'm so lazy to create models, but I would recommend you people to try it out. So think of a scenario where you have a door, right? A door to enter your house. Let's say this is your door, right? Now, if at all you want to enter your house, this door must be open. Only when you open the door, you can enter the house, and you can maybe turn on a lamp that's around in the house, right? Now, when you have a single door, there's just one pathway. You reach your house and you can turn on the lamp. But what if you have two doors like these? So you have one door here, right? Another door here, which means you have a choice to enter through this door or through this door to turn on the lamp, right? So you can enter either via this door or this door. So let's say you enter via the first, you don't enter the house at all. The lamp is not on, but maybe you enter via the first door. You don't enter via the second door. Then also you can turn on the lamp, or you can enter via the second door and turn on the lamp and not via the first door. So the pathway that you enter, that's called that as 1. And the pathway you don't enter, we can represent as 0. So when you look at this particular scenario, the possibilities are these. So this, we call this as a truth table. So let's say there is door 1. and door 2. So let's say when you have 2 doorways, the possibilities for you to enter is you don't enter in door 1, don't enter in door 2. What is the status of the lamp? The lamp is not on, it's off. So let's represent the lamp status off as 0, and you not entering a particular door also as 0. So when you don't enter either of these doors, obviously you cannot turn on the lamp. Another option is you enter via door 2, which means you don't enter via door 1, but you enter via door 2, you can turn on the lamp. Or you can enter via door 1 and not via door 2. Even then you can turn on the lamp, right? Even then you can turn on the lamp. Just a second. Of course, what if there are 2 people, right? Not just you and your friend. Both of us and both of them enter via door 1 and door 2. Either one of them can switch the lamp on. This is an OR gate. This is called as an OR. You can say either go this path or go this path, and you have the result that you wanted. That's why it's called as a OR gate, right? It's a logical OR scenario. However, if at all you have a gate, if you have your doorway organized like this, let's say you have your path to your house, maybe a foyer or whatever the house, and the pathway comes with 2 doors in this particular configuration. You have door 1, then you have door 2, right? And then you have the lamp that you have to turn on. Now, here's a scenario. If you don't enter either of the doors, the lamp is not turned on, right? You don't enter either of the doors, the lamp is not turned on. You could open this door, but not open this door. That means you cannot enter in. Obviously, lamp is not turned on. If you leave this door open and this door closed, even then you cannot enter in, because if you have to enter, you have to first have this door open. Am I right? So only when you have the first door open, you can go to the second door and you can turn on the lamp. That means for the lamp to turn on, you have to turn, if you want to turn on the lamp, you need to go through both the doors. That means both the doors must be passed through. You have to open both the doors and enter in, right? And this configuration, we call this as the AND gate, because you have an AND scenario. This and this, both doors must be opened, right? And the truth table for that would look like you have 0, 0. That means both doors are closed. The lamp will remain off because you can't enter in to turn on the lamp. If maybe you have one door closed, another door open, still you cannot reach out to this room to turn on the lamp. Even if you have the first door open, second door closed, even then you cannot reach out to turn on the lamp. Only when you have both the doors open, only then you can reach out to turn on the lamp. And this is a basic principle of an AND gate, which means both inputs must be on for the output to be on. Here, either of the input can be on for the output to be on in the OR gate. You can see that, I brought it on. Both these switches are off. Both of these are in 0 position. When both are off, let's call this A and B. Both A and B is off. You can see the outcome. This light is not turned on. When both of these are off, 0, 0, 0, 0, 0. It means A is 0, B is 0, output is 0. But when I turn on B is 1, right? Over here, as you can see here. When I turn on B here, turn this on, you can see output. I'll turn off B, I'll turn on A. Even then there's output. You can ignore this light, okay? This light doesn't glow, but this will glow, but it's okay. I need a DP switch to make it work correctly. You can see that. So 0, 1, as I mentioned, 0, 1 is 1. This is 1, 0. A is on, B is off. Even then, output is on. When you turn both of them on, output goes off. You can see that? When both the switches are on, or when both the switches are off, the output is off. Any one switch is on, right? They must be completely alternating. So one switch, at least one switch must be on, one switch must be off. When you have this kind of a combination, then you will see the output here, right? So it's output, the light goes on. This is actually called an XOR gate. Technically, it stands for exclusive OR, but it's also called XOR for one more reason. If I show you the circuit behind, you will see why it is called XOR. If you see the switches, these switches I have shown yesterday, these are switches with 3 pins, like this, 3 pins, not just 2. There's a common pin, and there are 2 sides here. So when the switch is in one position, it creates connection in these 2 pins. These 2 pins will have connectivity. But when I turn this rocker switch to the other direction, when I turn it on this direction, the contact between these 2 pins will be active. It'll make a contact between these 2 pins, not this pin, right? So that's how this particular switches work. This is called as some people call this as a 2-way switch, but technically it is a single pole double throw. Or it's also called as SPDT or SPST in the electronics terms, right? Single pole double throw or single pole 2 throw. Either of them can be used. So this kind of switch is what is used here behind. And you can see this. I'll just turn this off. What I've done here is that these 3 switches, right? These 3 pins are there, which you can see. Closely observe, you can see an X mark here, cross connection, XOR, okay? Cross connection. So when you have these 3 pins of the switch, the one end of the pin, right? One end of the pin of the switch, I made a connection to the other direction, opposite direction. This pin, I made it to this opposite direction. What about the common pin? One part of the common pin is connected to my battery. You can see it's connected to the battery, the negative side of the battery, right? Negative side of the battery. And the positive side of the battery goes through the LED. Okay, the LEDs come out. You can see the LEDs come out. Goes through this LED light, through a resistor, of course, and then reaches out to them. There's no resistor for this because it's a green LED. Green LED will work without a problem in a 3-volt battery. Generally, the activation voltage will be around 2.8, 2.9 volt. You don't need a resistor. It just works. Of course, having a resistor is generally a good idea, but yeah, I just use it without a resistor for now. I'm not turning it on for long duration, right? So it's connected to this side. So if you look at the circuit for this, this is how the connection would be. An SPDT switch is actually generally represented with 3 points like this, indicating the contacts, because the 3 pins, the common pin and the 2 side pins like this, okay? There are 2 SPDT switch. I'm going to put them this way. 2 switches. So the switch could be connected in one direction here, and this could be also connected in one direction here, okay? Now, what I've done is, this pin I've connected to, cross-connected to this pin. And this, as this other side, the other pole, right? Other pin node here, I've cross-connected to this pin. I've crisscross connection. This common pin, one common pin, I've connected to the negative, the black wire, right? To the negative of the battery. Let me just put the battery like this. And the other side of this common pin, what I did was I connected to an LED in this direction. This is an LED, right? And then the other end of the LED, I've connected to the battery like this. Now let's look at the circuit now. When both these switches are on, both switches are on, okay? Let's say the top side is on, bottom side is off for now. When both switches are on, is the circuit complete? Let us see. Current flows from this positive side, goes to the LED. From the LED, it reaches till here, and then it reaches at this point. The circuit is not complete. Am I correct? Because there's no connection. The connection, it's an open circuit. This is an open circuit. The circuit is not closed. Why? Because it has to connect to negative. It is not connected to negative because the switch is not connected in this configuration. When I have both of the pins or both of the switches on, same direction, the current flows from the positive, it reaches all the way here, reaches onto the LED. From the LED, from the light, it goes on to this pin of the switch, the corner pin of the switch. And that corner pin is cross connected to the opposite corner pin on the other switch. And this opposite pin is an open connection, right? There's no connection to this. So this is an open circuit. So this is the reason why the LED does not glow when both the switches are on. I'll tell you about all these basic gates, but I will show you that these gates can be constructed using relays. First, I'll demonstrate using a relay. This relay, this same circuit. You might ask, some of you who are not seen this before might ask me what this is. This is a breadboard. A breadboard is a very nice prototyping board where you don't have to worry about soldering ions and everything. Remember, I connected gates with switches and alligator clips yesterday. You know, when there are a lot of connections, this whole thing gets very messy and it's very difficult to remember where the connections are. A breadboard allows you to cleanly lay out your circuit without having to solder them. That means you can remove these components, reuse them again, and all this. See, all these components can be removed. I can remove this component, all this. I can remove this LED, for example, put it back in here. Right? So I can reuse these components, prototype them. So when you're experimenting with electronics, having a breadboard is really, really useful, really handy. Okay. So most of these components that we buy, any component, through hole components can be actually laid out on a breadboard. Most of the components are breadboard friendly. Okay. So I talked about all these. This is a same circuit using a relay, but it's just a demonstration here. Okay, this requires a slightly high voltage. Battery voltage will not do. I need a 12-volt adapter because this relay is rated as 12 volt. So it doesn't work with low voltage. But I'll explain how this relay works and everything. Okay, so don't worry about that. But just let me show you the functioning of this. And then I'll explain the bare fundamentals of relay module and show you how they actually work. You can ignore this for now. This also is one gate. There's a gate over here. This gate, right? There's only one input. The switch acts like input. There's a push button. When I press the switch, you can see it goes off. Remove the switch, it comes back. This is a NOT gate. NOT gate is reverse. If the input is 1, output becomes 0. The input is 0, output becomes 1. That's why it's called as a NOT gate. It's a NOT operation, right? I'll explain that in a while. This is just a simple gate. These two relays are like switches connected in a configuration of an OR gate, which I'll explain here. Just see, if one of the input is on, output goes on. This is one input. This light indicates another input. This light indicates an output here. If one of the input is on, output is on. See, I can turn on this input. I can turn on this input, but I can turn on both of them. I can have to press both the switches. Both lights, both inputs are on, output is on. One input off, output is on. This input off, output is on. Output is on. Only when all the inputs are off, you see no output here. But instead of having mechanical switches where I have to flip things, I'm using push buttons here. And you can see it activates the relay. You can see some mechanical movement. You can see this. I'll show it to you here. The switch, right? Here's a switch. Here's a switch. Currently, this is like a spring. There's a center entry, right? It's like a spring. But I press the button, just see the movement. Do you see the movement there?
Yes, sir.
This is what we call as a electromagnetic relay. Electromagnetic relay. These are switches that can be operated by electricity itself. You might ask me, why do you want to do this? I can turn on the switch directly, right? Why should I use the relay? I can use this rocker switch and I can press the button here. Anyway, I'm pressing a button here, right? So the same thing I can press in this itself and make it work, right? What is the use of this relay, you might ask? Now, the advantage of the relay is that there's a coil here. Do you see this coil? It's a coil of copper. It's very similar to, now we'll talk about conversion. If you're to convert a decimal number to binary number or binary to decimal, it's a challenge. How do you do it? If at all you want to convert from, let's say, a binary number to decimal number. Oh, first I'll talk about decimal to binary. That's easier, right? So let us say I want to convert 17 to binary. The value 17, I want to convert to binary number. How do I convert it? The mathematical approach to it is pretty straightforward. You divide this 17 by 2. I'm using this notation. Some of you use the proper division notation. Standard change. Okay. I learned it like this in my school days. Okay. So you might have learned some other way. It's okay. So you divide 17 by 2. Once you divide it, what will it go by? Yeah, what's the closest? 8, right? 2 8s are 16.
Sir, it is 8.
1 is remainder.
Sir, it's 8.5.
That's correct. Oh, don't use decimal. I don't want to do decimal division. Not decimal division. Okay.
Sir, the
That's correct.
remainder is 1.
Remainder is 1. You divide by 8, keep the remainder here. This remainder is what is very, very important. That's what creates a binary number. Now what you do, you divide 8 by 2. So what do you get? You get 4,
4.
remainder is 0. You again divide 4 by 2. What do you get? 2 2s are 4, remainder is 0. Then what do you do? You divide 2 by 2. 2 by 2. So 2 1s are 2,
Sir,
remainder is 0. So what is the value? The value is you start counting like this in this order. 1 0 0 0 1.
sir,
Sir, it is easy.
sir, so repeated division is basically how you get the binary.
Exactly. Repeated division. Once you repeatedly divide by 2, you take each remainder and the remainder is what you'll be using.
So, but how did the extra 1 come at the end?
Oh, because 2 1s are 2. The last
Oh.
quotient is also taken into consideration. Not only the remainder, the last quotient is also taken in. That's one important aspect. Okay. So if you just want to, this is how this binary number is. Actually, if you start counting in sequence, right? Binary sequence, just see this. I was counting binary sequence here, right? I was counting up to 15. 15 is what? 1 1 1 1. What is 16? 1 followed by 4 zeros. What is 17? 1 followed by 3 zeros and 1. We got this, right? Right? Sorry about this. We got this, didn't we?
Sir,
Clear? Yes.
how do we convert binary to decimal, sir?
That's a good question. Now, this number, I want to convert it back to decimal. Somebody gave me this number. I don't know whether it's 17 or 23 or 44. I don't know what it is. I want to convert back to decimal. How do you do it? The shortcut, I will tell you. Shortcut, okay?
Sir,
You
the
take this
base
number.
is 10, right?
This is base 2. This is base 2. Base 2 number system. Binary, right? So this I want to convert to decimal format, base 10. You want to convert to base 10 or decimal format, put these numbers like this. From the right side, you start counting like this, okay? This is called log 2 counting or power of 2 counting. You put 1, next value is 2, 2 plus 2 is 4, 4 plus 4 is 8. Remember, 4 plus 4, 8. You have to keep doubling it up. 4 plus 4 is 8. 8 didn't come up correctly with this marker. Okay, 8. Sorry
Sir,
about this.
then 16.
Then 16. Wherever you see 1, right, carry that below here. You see 1 here, carry that below here. Add it, you get 17. It is the same as
Sir,
16
even if
into
you-
1 plus
Hello,
8
sir.
into 0 plus 4 into, in your school mathematics. So I told you the terms use, some terms you should know. In binary, right, each digit in a binary number is called as a bit. So we look at this binary number has 5 bits. There's a term used, 5 bits, okay? If you group 4 bits together in a binary number, we call that as a nibble. 4 bits make a nibble. If you group 8 bits in a binary number, we call it a byte. B-Y-T-E, not B-I-T-E, okay? So we say bytes, right? Kilobytes, megabytes. What is that byte coming from? It's about how many bits you can store, how many binary digits you can store. If I say my pen drive is signed numbers, right? If at all I want to represent signed values using the binary number system, the way it is done is by sacrificing the most significant bit to represent a signed value, right? So if at all I want to represent a number using 4 bits, right? If I'm going to use 4 bits, then let's take this number here. You can see the table, I guess, all of you. Okay. I just put up a table for convenience. If not, I want to represent 0, 0 does not have any sign. So it is all zeros here, right? 4 zeros. This is represented as 0 in the signed value. The unsigned representation is also 0. That means if you try to treat all the 4 bits as a number, then it is treated as an unsigned value. When you use a signed number system, when you sign numbers using, you will not consider all the bits for the numeric value. You'll only consider the 3 bits here for representing a number, and the most significant bit that is there, which are colored in dark green, if you can see, is actually representation of the sign. If the most significant bit, that is the first bit that you see here, is 0, it is indicative of a positive number. For a value called 0, there's no positive or negative, so you can ignore that. But if you consider 1, 0, 0, 1, this is treated as +1 because the most significant bit is 0. Okay. If at all I want to represent 2, in binary is 0, 1, 0. But it's treated as +2 because the most significant bit is 0 here. Same goes with 3, 4, 5, 6. Maximum value you can count with 3 bits is from 0 to 7. Though you're using 4 bits, because I told you 1 bit is not used, it is for representing sign, you're only left with 3 bits to count. So which means you can count from 0 to 7 on the positive side. But what about negative values? To represent that a number is negative, you make the most significant bit 1. The most significant bit is 1. It is an indicative that this number is a negative number in signed value representation. What are the ingredients of the brain of the computer, right? I told you the brain of the computer is the CPU, right? The central processing unit, which does all the activities that you know about a computer. You know about the CPU, like you say, I have an Intel Pentium Pro. Pentium Pro is my generation. Okay, you people might say Core i9, right? Or Core i7, 8th generation, AMD Ryzen. You'll use all these brands. Or if you use a smartphone, you'll say, my phone has got a Snapdragon, whatever model that is, right? Snapdragon 630 or 820, whatever number. Okay, I don't remember the numbers. I'm not clued into those brand numbers these days, but you brand each phone based on how fast and powerful the CPU is. Now, what are the essential ingredients of a CPU? Well, I should tell you right now, what I'm telling you right now is a very bare essential. Many CPU manufacturers hide a lot of details. They won't disclose it to us. Okay, that's a real fact. But what we need to know as a programmer is this much. What is exposed to us, right? If you consider a CPU has all of these components. We take this as a CPU. We also call this as a central processing unit. Sorry for my bad handwriting, because I rarely write these days, decades. I mean, only typing, not writing for decades now, right? So a central processing unit, the major part of it is something called as an ALU. ALU is represented symbolically like this by most CPU designers. Looks like a half trouser. Okay, yeah, this is an ALU. ALU stands for Arithmetic Logic Unit. Arithmetic and Logic Unit. The job of ALU is to do all arithmetic operations and logical operations. When I say all arithmetic operations, what all arithmetic operations can it do? In reality, only one operation, addition. That is it. It is a big, shocking revelation. An ALU contains just mainly an adder. It just adds numbers. It knows only how to add numbers. If you know how to add numbers, you can also subtract numbers if you represent a number in signed format. If you represent -3, -8, all these numbers, right? You can just add the negative number, the positive number, you get subtraction, right? That's how this ALU is designed to be. Now, the main component of ALU is an adder, and then it also contains a comparator. A comparator will compare two values. You give two values to a comparator, it will say whether one value is bigger, the other value is bigger, right? So it'll just compare two values. Suppose if you just provide like something like 0 and 1, it'll tell you 0, or 1 and 1, it'll tell you 1. Both inputs must be on. So it'll tell you which one is big out of a value, right? So that's how it does. So this is a comparator that is there. But now this ALU is connected to something known as registers. Registers are represented like this. What are registers? Registers are a kind of, you can say it's memory, right? It's a very minimalistic kind of memory. So your memory is actually, you can think of as like gigantic set of registers in a way, right? I'm oversimplifying it. In reality, the actual design of a register might be very, very different than the actual design of memory. Cost and everything matters. So yeah, but they serve the same purpose. They store data. They are mostly used to store operands. See, if at all I want to add two numbers, if you want to add, let's say 0, 1, 0, 0, if you want to add it with, let's say 0, 0, 1, 1, I want to add these two numbers. These are the operands, right? The 0, 1, 0, 0 is an operand. 0, 0, 1, 1 is an operand. See, in arithmetic, when you say 4 plus 3, this 4 and 3 are together known as operands. And the plus symbol that you see here is also called an operator. Instead of plus, you can have minus, you can have multiply, you can have divide. All these are operators. These values, which are trying to add or subtract or multiply, these are called as operands, right? Now, basically what happens is that the registers are used to store the operands for stores operands for arithmetic. Right? Now, basically, if at all I want to add 0, 0, 1, 0 and 0, 0, 1, 1, I should store 0, 0, 1, 0. Sorry, 0, 0, 1, 0, 0, whatever number it is, right? Must be stored in one of the registers. And maybe 0, 0, 1, 1 must be stored in another register. And then you have to pass on one value of the operand to this ALU, another value of the operand to this side of the ALU. ALU takes two inputs. And the ALU will compute and store the result, maybe in another register in some CPUs, or replace an existing register in some CPUs. It depends. Depending on the CPU design, maybe the first register will be replaced with the result of these two operations, or maybe it will store in the third register.
Sir, so the registers will store the number. See,
Yes.
binary
Exactly.
digits.
Yes. The register stored the binary digits. The next class, next Saturday, I will actually demonstrate how a simple register to show you how a register stores value. I will show you a simple adder to show you how it can be added. So the basic stuff I will tell you on the next class, right? The next, I'll show you the electronics that goes on to it, albeit as demonstrations. With this time, I'll use ICs to show you. Okay, so integrated circuits to show you. You can also do it with relays and transistors. It'll be more complicated, but I'll just show you with simple ICs. So this is how the registers are made to store this number. This register is made to store this number. And then you have to somehow tell the ALU that you have to add these two numbers, not compare, but add, right? Once you add them, the ALU will add it and store the result in here. Maybe 0010 plus 0011. It's actually 2 plus 3. It'll be 5, right? It'll be 0101, right? This will be stored here. So this is how computation happens in a CPU. Now, somebody has to guide all these, right? Somebody has to instruct the ALU to pick this value from this register, pick another value from this register, and then tell the ALU to add these two numbers and store the result. That is done by another component called as an execution unit. Shortly called as EU, an execution unit. This is another component. What does it do? The execution unit will take program instructions from memory, and based on that, it fills up the registers and then tells the ALUs to add it. This execution unit is responsible for connecting to the actual RAM, or the random access memory that we have, or system memory that you have. Which might have your program. See, for performing this operation, right, you need to write a program. Even the basic operation in write program. If you remember in the Python class, the first class, I was showing you some machine language and assembly language. I had to go and retract the slide, maybe. I hope you can remember this slide. In the Python sessions, I think in session 8, I think I talked about this. I told you what a machine code looks like.
So you showed this slide in session 7 or 8.
Session 7 or 8, I think. Yeah.
Yeah.
I think I can see it in session 8, actually. I started
Yeah,
look at it. So this is actually what we call as machine instructions. These machine instructions are nothing but just bunch of binary numbers which are stored in RAM, which you store into RAM. How you store it and all these, it's a big topic. We'll discuss next step. We'll talk about that. So once you load a program into RAM and tell the CPU to execute this program, the CPU will start fetching, generating a location in RAM, right? It generates an address. Your RAM is made up of addresses. You say 0th location, what is it? First location, what is it? Second location, what is it? Third location, what is it? The job of the execution unit, it works with something called as a, instruction prefetch unit, which will actually do, which will coordinate with execution unit and say, okay, which is the next set of instructions that fetch from RAM? Will fetch that instruction. The execution unit will basically look up what instruction it is. If the instruction involves loading a value into the register, this is a load operation. This is a mnemonic in Intel platform to load a value into a register. This is like telling move. Move is nothing but move something, right? Move a value from memory, that is from RAM, right? What value you want to load? A value like this is an immediate value. It's not a value from RAM. This is an immediate value, right? Load a value called 0x1 into this particular register. And then load 0x1, let's load 1 into this particular register. These are registers are given names. For now, I told you about arithmetic expressions last class. When I say 4 plus 3, you get the value 7, right? It prints 7 here to indicate that this is a result of this expression. You can put any kind of arithmetic expressions in here.
Sir?
Now, one of you asked me how to.
Sir.
Yes, go ahead.
If you put the 3 numbers, if you add that to the same 3 numbers, it come error, sir.
You may say 3 numbers, right? Let's say 4 plus 5 plus 6, something like this.
No, sir, the 3-digit numbers.
3-digit number, no problem. You can put 3-digit number. You can just say 1, 2, 3 plus 4, 5, 6 plus 7, 8, 9. It works. It will not throw any errors.
Okay, sir.
The only thing, all right. So let's talk about variables, types, and objects. And we all learned what a variable is, right? In Python, I told you we label everything using a name, which we also called as a variable. Like we did it here, right? We can say score is equal to 4.7. So here, I hope the Tawny window is open. Yeah, you can see that. I'm running on a virtual machine. So if you just go to this shell and say score is equal to 4.7, this score is called a variable. This
Sir?
is also called as a value.
Sir,
Yes, Aditya.
computer has only 2 digits, 1 and 0 and 1, sir.
Exactly. That's right.
Sir, then why in the keyboard it says 1, 2, 3, 4, 5, 6, 7, 8, 9, 0?
Oh, that is for our understanding. When you type something on the keyboard, all the alphabets and numbers, it is for our understanding. We see, okay, 1, 2, 3. We humans, we like decimal number. That's why we put that on the keyboard. But when you press these keys are converted to binary numbers and fed to the computer. Understanding it? So all the keys that you type on the keyboard, they're converted to binary numbers.
How is it converted to binary numbers?
Oh, by using circuitry. This keyboard has got a small microchip in it. And this microchip, see, it's a switch, right? You have a switch when you turn on and turn off switches, right? When you press one key, it actually is one switch. When one switch turns on, instead of giving 1, it'll give you numbers like, 0, 0, 1, 1, and 0, 0, 0, 1, or something like that. When you press the number 2, it may be 0, 0, 1, 1, 0, 0, 0, 1, 0, 0. It goes on like that. So it gives you different number combinations when you press all these keys. And the computer say, oh, you press this key, I press this key. And then there are programs in the computer that will actually try to decipher what keys you press and decide, oh, you press this key. This is supposed to be 1 in human way of thinking. So let's treat that as 1. They'll store 1 as binary numbers and they'll do this math if necessary. So there's a microchip inside the keyboard with a matrix of switches. This is where this keyboard that you see here, like what I'm showing you. This keyboard that you see here, it's got a matrix of switches. All of these are switches, push buttons. And when you press each of the switch, the switch will actually activate the microcontroller or microchip inside it, which will give a sequence of a number. It's like, which key you press, how do you identify? You have to give some numbers, right? These are called as scan codes. Scan code, you call them. It's like row and column. You press rows, you press the, row 0, column 1, row 2, column 3. So they're treated as, rows and columns, and the row column combination expresses binary numbers and fed to the computer. And the computer has something called an operating system, which is a program that boots up your computer. When your computer boots, it comes with loads an operating system program, and that basically tries to understand all the keys, scan code, which I press, convert it to the appropriate digits that humans sort of, use and perform activities based on them. Okay.
So sir, if we put all those bin of n plus m, hex of n plus m into like in the brackets of int function, then will it work?
No, it did not work for me.
If you want to put it in, no, I don't think that's why it didn't work. I think I'll tell you, I'll figure out why it didn't work. Let me just type it off correctly. I think it's all in different lines, right? And say O is equal to, you put it like this. You said bin of n plus m plus oct of n plus m plus hex of n plus m, and you close quotes like this. And you try to print n plus m plus o. Oh, okay. This statement is not an error. This statement is not an error. But this statement is an error. I'll tell you, if you just print O, it'll work. You print O, right? It'll work. See? But then what is O exactly? O is a string. O is a string. Getting my point? I'll tell you. I will also, this might be a little jumping forward. Next class, I will recap this to others. Okay. So it is like, if at all you want to find out what is the type of the value, right? Type of the value that the variable is representing, you can use a type function. See, type of O will tell you if it shows str, it means it is a string. See, it shows string.
Okay, so str means string.
Yes. Str short name for string. So if you say type of a variable, it'll tell you what value type it is, right? What value, what type of value belongs to. For example, if you just type of n, right? And I'll say type of m. See, all these are what? It will show up as class integer. So what I did was, I put from machine, import pin, and first I did LED is equal to pin of 15. Mode is equal to pin dot out. Made this an output pin, and I said button. If it's difficult to type BUTTON, you can also use B, or you can use BTN, whichever you find convenient. Some of you struggle typing, you can use short names. You can use L and B if you want to. Okay, so it's all labels. Labels can be anything that you choose, right? It's nothing wrong in choosing whatever label you find convenient. And you can use pin of 14. Mode is equal to pin dot in. So this is, first one is an output pin, second one is used an input pin. And then I try to print, if at all I try to say LED dot on, LED dot value. So LED value of 1. So I'll just run this code. And I'll do one thing. I'll also use some sleep here. Okay. I'll also add a line here. From time, import sleep. Okay. So I'll say LED value dot 1, value of 1, and I'll put a sleep of 2 seconds. And then say LED dot value of 0. When I run this program now, as soon as I run this program, the LED will turn on and leave it on for 2 seconds, and it'll turn it off automatically. See, LED is on. 2 seconds later, the LED is off. Right? So you can see that. Now what we'll do is that I want the LED to turn on when I make contact on the switch. I press the button, that is. When I remove the contact, I want the LED to turn off after 2 seconds. And how do I do that? Well, first, I can just do it continuously. I can put a loop here. I can put a loop. While true. This is an infinite loop. In this loop, I'm going to use a condition. Okay. If button dot value equals 1, if the value of the button goes 1, then I want to turn on the LED and keep it on for 2 seconds and then turn it off. Okay. So instead of 2 seconds, I can also make it, let's say, 5 seconds. Okay. I will close the shell for now, so I can see the entire code. And then, okay, I think that's just be fine. I'm just using that condition. If the
So don't you
button
think we
value
should
goes,
put a sleep even after LED dot value 0? Otherwise, you will not be able to like see what happens.
because anyway, we are turning it off after 5 seconds, so it's okay. We'll see. Okay, so we'll run this program now. Okay, we'll see. And then you can improvise after that. Now, when I run this code by default, okay, the shell is closed. I'll have to view the shell. This code is running. Nothing's happening. Nothing's happening on the board. Now, just observe what happens. When I touch these two ends, right? The moment I touch, just see what happens to the LED. It's a LED, oh, the LED glue. Because I touched it like this, it glue. See this? Because my finger is carrying value 1. See this? Ideally, what happens is that if it doesn't work, when you touch it in your finger, this one, you just take the supply pin, touch it here. See? It goes on. 5 seconds later, it'll turn off.
Sir, after turning off, why doesn't it immediately like turn on again?
The reason is because, see, look at the logic here. This loop will run forever, continuously. See, the program is running. The program right now is fully running. It's continuously running. What is it doing in this loop? Continuously checking the value for the button. It's calling what is the value for the button? What is the value for the button? The button value is 0. This condition is false. The button value is 0. The condition is false. Because the condition is false, it will not execute any statements inside this block. Do you see how I'm using condition over here? I'm checking whether the button value is equal to 1. When will it become 1? Only when I connect this to wires. The moment it becomes 1, turn on the LED, leave it on for 5 seconds, then turn it off.
Sir,
Right? Yes.
sir, so can we add one elif? So if this thing doesn't work, so we can add one more elif button dot value is equal to 0. Then run this thing.
Yeah, you can also do that. You can also put that. See, you don't need elif. You can just use else because a button only has 2 states, 1 and 0. When you only have 2 states, you can use if and else.
Okay.
Raining, not raining. On, off, right? When you have 2 states, if else is sufficient. Maybe you have more sophisticated system where it gives you different values, 1, 2, 3, 4, and all, and you want to, based on that, you want to do some manipulation. That's where you need to use if elif. If the state is this, do this. If elif another state, do this, right? You can actually have multiple states in such a case. So what we have created here is a time switch. Imagine this. Sometimes when you go to let's say you just go to a room. As soon as you go to a room, you press a button. You want the light to be on, not forever. Only for 10 seconds, you want the light to be on. After that, it should turn off automatically, right? Delayed turn off, right? We got that. So instead of 5 seconds, I can put 10 seconds here. It doesn't matter. You can put 10 seconds here. And I'll just see the same code. I'll just stop and rerun the same code again. Let's call it as rect area. Area of rectangle, right? Which takes length and breadth. And we are just going to return length into breadth. Now calling this function, you can call it like this. That is, you can say rect area of, you can say 10, 20. And actually, if you remember, I told you last class that passing parameters like this is called calling a function with positional arguments. When I say positional arguments, what it means is that I am actually passing the first argument as 10, second argument is 20. The argument names are not mentioned. First argument is 10, second argument is 20. Only when you know the function prototype. What is a function prototype? how I define this function, I will know that the first argument will be assigned to a variable called length. Second argument, whatever you pass 20, will be assigned to breadth. And the function is executed, which will compute 10 into 20, this length into breadth, right? But suppose if at all I have a function that takes multiple parameters, maybe I want to pass the breadth first and then the length, right? I should be very specific. To make it more specific, you would use a syntax where you say rectangle area of breadth is equal to 20, length is equal to 10. In this function, it does not matter whether you pass length, breadth, or breadth, length. Multiplication 2 into 3 or 3 into 2 is the same, right? There's no difference at all, right? Whether it's a 2 into 2 or 3 into 2, it's a 2 into 3 or 3 into 2, both mean the same thing. So in this case, it's fine. Last class, if you remember, I think I showed how you can actually control a simple 7-segment display using MicroPython through Raspberry Pi Pico. We in fact did the wiring and everything, right? And I think I showed you what a 7-segment display looks like you see here. Like you see here, right? So 7-segment display, I think, yeah, here it was. We connected all these pins. I noted down the pins that we connected on the Raspberry Pi Pico through the 7-segment display through these dropping resistors. And we also wrote a program to control it. And just to recap the program that I wrote, for this, I need to share the screen on my Windows. Just one moment. Remember, we wrote this code last class, right? We wrote a function to display something on the 7-segment display, and we also tested it. In fact, if you run this code, you'll see that on my other camera, you can see that display will be lit up. So if you just run this, you can see it's running a counter, right? All this is done through a program. We did it programmatically. This code that I wrote had this complete layout for displaying various digits, right? So each digit is, we call them as a segment. That's why it's called as a 7-segment display. There are 7 segments in it, along with a dot that makes up the 8th LED in it. And we say which LED must be on, which LED must be off for different numbers. So if you want to represent one number, what displays must be on? I think it's for 0. For 0, you need to turn on all the surrounding LEDs. I think this is a layout, right? We can see that right here. So we can see the surrounding layout. We can say A, B, C, D, E, F must be on for 0. For displaying 1, we need to only make B and C on and keep everything else off. So this is like a bitmap, which I just showed you on for different digits to be displayed by turning on and turning off LEDs accordingly. And we wrote a small function to manage it completely. We wrote a function called display. And in the main boilerplate, I showed you how you can display this entire thing. Now, as I told you that this is a proper candidate for object-oriented design. So what exactly is object-oriented design? I think Deepthi asked me this just before we started and it sort of spilled over. See, when you have some variable that represents some data and you have some function that's operating on that specific data, and you believe that the function only operates on data nobody else does, it's a good idea to modularize them by adding them inside a class. How do you create a class and put all of these things inside a class? I will just show you right now. So if this whole code, I'm going to save it. I'm going to save this file as and now,
Sir?
yes,
Actually, I did not do that in the way you were doing, like A, B, C, D. I was doing like the position where the pins of the display are.
that's correct.
Like the
Yeah, you
pin
can.
numbers, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah, you can.
I did it in that order.
Yeah, when you do it like that, Shivan, see, you will use it. Somebody is going to utilize your class will find it difficult to use. It's always, when you're designing classes, you always think about making it easy for someone to use. Always.
Because for me, I find it difficult to like label them with A, B, C, D. Because you
No,
don't know, this is A, this is B.
no, when you say pin config, the pin config has this entire thing wrapped in, right? It's easier. It's much more easier. Okay. So, I mean, you can change, you can also say 7-segment display off. You can say A, comma, B, comma, C, comma, D, comma, E, comma, F, comma, G. You can pass it like that. But as I told you, that is not a good interface design. See, when you're working with any equipments, we always like less controls, right? What is easy to learn, whether driving a car is easy or riding or maybe flying an aeroplane. Well, obviously driving a car, right? So if you want to drive a car, all you need to know is how to maneuver the steering, how to turn on the ignition, how to manage the brake, accelerator, and the gear, pedals, and all that. Very simple. Not very simple. It's better. Okay. Riding a bicycle is even more easy. You need to know how to balance your two wheels and just pedal, right? And maneuver your handlebar. But flying an aeroplane is challenging because you have a lot of controls. You ever seen a Boeing aircraft's dashboard? You'll see a lot of buttons. That's why becoming a pilot is not a very easy thing, right? It goes through a lot of rigorous process. The point is, people like simplicity. Why people don't have? Why don't we have flying cars as yet? Simply because flying a car is not easy. On our own, flying a car is not easy. It requires a lot of maneuverability. So people like simplicity. So when you're designing anything, you have to keep your interface simple. Interface is what? How somebody is going to utilize your object. That must be very simple. You should always plan on that, right? So I would find using a class that takes lesser parameters in the constructor is much easier than having 7-segment display with like 7 arguments and 8 arguments. That's why I chose this. Okay. So again, it's a choice. It's a matter of choice. Okay. So when I say instance method invocation, instance is a technical jargon for objects that belong to a certain type. Digit is an object. Digit is a variable that represents an object that belongs to a type called 7-segment display. Type or class mean the same thing in Python. Okay. So when I use the word type or class, it means the same thing. When I say a is equal to 10, we say what is type of a? We say it's an integer because a is equal to 10 is an integer. We say type of a will show you integer, right? What is integer? It's a class. Class and type mean the same thing. So 10 is an integer, we say. When I say a is equal to 10.0 and say type of a, you get float. What is that? It's a type of that variable, type of the object that the variable points to. That's 10.0. Similarly, we are creating our own type here. We are creating our own class here, which is called 7-segment display, which is what we created in the other file that I showed you in the other tab. And that particular class, all the methods or all the objects of the class should support show method. Show as a function, right? Methods are functions which are specialized to operate on an instance. And that is called as instance methods. In order for invoking instance methods, you say the object and put a dot here. And then you say what method you want to call on that object. It's like in real world. In real world, when you look at object, let's say I have a mouse here. I have a wireless mouse here. Mouse dot click. How do I say? Mouse dot click. I can only click on the mouse. It doesn't make sense to, let's say, click on my smartphone. Smartphone, I can only do touch, no click. There's no click on the smartphone. There's only touch on the smartphone because I'm using a smartphone here. Or if I'm using, let's say, a pencil, this pencil I cannot click. Or some people might have a clicky pencil. We don't know, mechanical pencils, but this pencil I cannot click. What I can do with this pencil? I can write, I can sharpening the pencil with a sharpener. That's right is a method that changes the lead, right? The lead which is there, which is longer lead will become shorter when you start writing it, right? The lead which is sharp will become blunt. And eventually when the lead is completely off, what do? You'll have to sharpen it. You have to use a sharpener and sharpen it. Sharpen is also a method. You cannot sharpen, you can sharpen a pencil. There's no point of sharpening a mouse. You won't take a mouse and put it in a sharpener, right? You won't sharpen a mouse. So these are functions which are tied down to the object. They work only on the object. What do they do with the object? Whatever ingredients are there in the object, that is called the attributes of the object, that state is changing. When you sharpen the pencil state is changed, right? From a blunt pencil becomes a sharp pencil, right? When I have this mouse here and I power this mouse off, this is a wireless mouse. If I can see it's glowing in RGB. When I power it off, what happens? The mouse state is changed. It is powering off the mouse, not my computer. The mouse is powered off. So these are functions that are designed to change the state of an object or work on the state of the object. So that's why they're called as instance methods. Instance methods is the Python way of telling objects' own functions, right? Objects' own functions. Clear? So when you have functions like, say, pencil, I can say sharpen and write. And mouse, I can use point and click on a mouse. But I can throw this pencil. I can throw this mouse. Don't want to do it, but I'm just telling you, right? The throw is what? Throw is not a method. It's a function. So this function, when I say throw me a pencil, throw the mouse to me. Somebody sitting that side, far off from me. So if I want to just hand over a pencil, one I can walk and hand over, or I can just throw and the other person will catch. I can catch the pencil. I can catch the mouse thrown at me. I can also catch a ball, right? There's words like throw, catch we use in real world. What are they? These are generic functions. Even in Python, you are seeing a lot of functions. Print is a function. You don't say something dot print of something. No, you don't say that. Print is not a method. Print is a function. That function will take anything you pass. It'll print it on the screen. Anything you pass, right? Print, you can print a list, you can print a tuple, you can print a dictionary, you can print a number, anything you want, you can print. Just like throwing, right? It's saying print this, print this, print this. You're doing that. So that's a function. So functions are designed to be generic in nature. Methods, on the other hand, will have a dot operator before it to say on what object they work. And the object is represented by this variable digit. Digit is still a variable. It's a label. I created this variable here. So I know it represents a digit. I called it digit. Okay, you can call it digit, you can call A, you can call B, you can give any name you want. Variables are identifiers. You can give any name you want. But what does it represent? It represents an object of 7-segment display or instance of 7-segment display. You have a class and you have an actual instance. When we say that we are all instances of human beings, that's the right thing. Human being is a class. I am a human being. You're a human being. All of you, right? I'm sure. All of us are human beings. Or some people might be superhumans, Superman, right? Just joking. So that's a different class. But I'm trying to say that if you're all instances of human beings. Similarly, if I say I have 100 pencils with me, what are they? They're all instances of a class called pencil. That's the term we use, right? Instance are nothing but actual object that belongs to a class. Everyone's clear about this? I'm making sure the jargons are clear, because when you use the jargons, you should know what it means. Yes. Go ahead.
Can you just go to the 7-segment display.oo?
7-segment display dot
Underscore OO, like 7_segment underscore display underscore.
This one.
Just 1 second.
Yeah.
I was. Okay.
I have not implemented it, not yet.
Okay.
We are going to do
Got
it.
it.
Okay, so we are trying to see all errors are coming up when you try to use it. First, you should try to use a class. Always, this is called as test-driven development. Test-driven development is an approach where, you see as a user, what is the best way to design your program. Always, when you're looking at object-oriented way, this is the best approach. You'll always think as a user and say, as a user, I should be able to create a class like this. I should be able to pass this argument. I should be able to invoke this method. Then what you do, you go and implement them. And as you're implementing, you'll see errors, and you have to make sure that you fill up all the gaps so that the errors are all gone. Okay, so this is how we are doing it. So now show actually takes no argument. We need to make sure that show takes 2 arguments. Why 2 arguments, you ask me? There's a difference between a method and a function. Functions are generic. Methods, they need to work on an object. So when you're defining a function inside a class, you should somehow tell the function on which object to work. Right? I can create like 4 different digits. I can say digit 1, digit 2, digit 3, all of them are different 7-segment display. On the Raspberry Pi Pico, I don't have that many pins, but it's possible that if I have some more set of pins, I can connect 1 more 7-segment display. I can create 2 displays. 2 7-segment display I can connect to 2 set of pins. I should be able to individually control them. I can control 1 digit or I can control another digit, right? So that means you can create 2 instances of 7-segment display. Now I should say, when I say call show, which one should I show on? First digit or second digit, right? How do I do that? That is passed as a first argument. We don't pass it, Python does it. Whenever you say object.method, object dot any function name, assuming that the function is part of the class, Python will always call that particular function, passing that object as first argument. And normally when you're trying to create any methods inside a class, which are called as instance methods, the first argument must be representing the instance. It's a common convention to call it self. You say show off self like this, followed by whichever number you want to display. You want to say show off digit, whichever digit, right? So I can just call this D or digit over here. I'll call this number. Okay, so I'll call this D, no problem. Self comma D. And yeah, I'm a little skeptical. If I use D, right, it's not very readable. So it's always better to use meaningful names here. Call it digit itself. Which digit you want to display? Now here, I'll save this file. And I'll try to run this. Still, I guess there should be one more error. Let's try to run this now. It's calling show as called, show as called, show as called. Actually, it's a little peculiar. If you had tried the same program on your standard Python, the 7-segment display of pin config, right? They should have thrown an error. MicroPython is not perfect in certain aspects. There are some rough edges. So right now, I pass pin config, and how do I get this here? I'm not getting the pin config anywhere here. The configuration of pins must be represented by the 7-segment display. I'm not storing anywhere. If at all you're passing any parameters to the constructor here, this is called as a constructor parameter, any constructor arguments to a class, in order to capture that, you need to create one special method inside a class, and that method is called as init. It's got a special name. You call it like this, _init, _ of self. Every function that you create inside a class by default should make sure that it takes self as a first argument. Okay. Everything else that you pass will be sent as second parameter onwards. Okay. So you'll say init of self, and then followed by whatever arguments, constructor parameters that you want to take in. So let's call this pin config here. And now I'll just try to print pin configuration. And I'll print whatever argument I got. Even for show, what I'll do, I'll say show was called. I'll say going to display. And what digit I'm going to display is this. Okay. I'm just adding those parameters in it. Now, when you actually run this particular program, the test program, you'll see the output like this. Do you see the output here? You can see that pin configuration 12, 13, 19, 20, 21, 11, and all these parameters, right? 19 and 18, whatever it is. You can see that. So it shows that the pin configuration is taken in, and then it's going to, because I'm calling show in a for loop, 10 times show is called. It's saying display, I'm going to display 0, going to display 1, going to display 2, 3, 4, 5, 6, 7, 8, 9. But then we are not implemented the way to display it. We are just printing on the screen. The real logic happens now. Now the real work begins. Normally in the init method, you initialize. Init stands for initialize. So if you want to initialize anything, if you want to initialize an object, you do it in init method. So as soon as you buy a new phone, let's say you buy a new smartphone, right? I mean, your parents would have bought it, right? When they bought a new smartphone, let's say you bought a new smartphone, what do you do with it? You initialize it. As soon as you power it on, you'll get some setup, right? You'll get some smartphone setup in which you'll go and fill in your IDs, install all the important apps, set up your contacts and everything. That's initialization. Then you can start making phone calls and taking calls and other things. Whenever you buy anything new, sometimes you have to initialize it. Even when you buy TVs today, smart TVs, you have to first initialize it. Today's TVs have become smart TVs. You have an Android TV, Google TV, Apple TV, whatever. So when you buy these TVs, what happens? They come with some standard default settings, but you want to initialize it. You want to set up your accounts. You want to install all the apps for different channels, right? We do that. So this is called as initialization. So even when you're working with any hardware device, as soon as you're connected to a device through software, we need to program it and initialize it. And we'll do that here. For a 7-segment display, the initialization is very, very basic. We are just going to initialize the pins. The pins are going to be initialized. And we do that. Whatever we did here, right? It is code. All these parameters, right? I'm going to take all these parameters. These go in the init method because we're initializing things here. So just copy this. I'm going to paste it inside this class. Now here, I have something called digits created here. The digits, right? Let it be at the class. This is some class specification, some data attribute for the class. Okay, so let it be as this. So make sure it's indented correctly. So let me just make it more beautiful. So I want to indent it even more. further down. So I'm just going to put a tab here. And then accordingly, there's a representation of A, B, C, D, E, F, G, H, E, F, G, and dot, right? So all these are shown here. This one, there is
So,
yes, Rishabh.
so can you paste like the numbers?
What-
Because I lost it because I didn't copy paste it.
oh, okay. Just one moment.
Just from the digits, yeah.
Let me just
Till
complete.
pins.
Yeah, okay, okay. I'll just
Okay.
copy this. Anyway, I'll complete the code and paste the whole thing. again.
Okay.
So, but I'll just because you're trying it, let me paste it again. One moment. Okay, where do I get my dashboard here? Just one moment.
Sir, can you put the code in the chat?
Yeah, I'll do that. I'm just do that. Just one moment. Just 1 second. I'm trying to see. Oh, okay, it's here.
Thank you, sir.
Yes, sure. Okay, let me put it on chat here. This file, I'm saving it as 7-segment display underscore oo.py. You can call it a 7-segment display.py also. No problem. Okay. Naming is up to you. You can choose whatever name you find it convenient. There was that other window. Okay. Got minimized. Yeah. So now what I was doing was this pins is there, right? This one, you should not keep it here. You should put this in the init method. So all actions must happen in initialization. So this is just initializing data. Data initialization, you can put it in the class. This will be common for all the objects. See if there is anything that is shared by all objects. For example, let's say that every mouse has a power on button. Every mouse will have it. Let's say every wireless mouse has a power on button. If it's a wireless mouse, power on button is there. That can be a class attribute. Even that also is not a class attribute because power on, power off will vary from one mouse to another mouse. I would say the right way to put it is the price of this mouse is a class attribute. The price. So if the mouse price changes tomorrow, if somebody had already stocked that mouse, right? Suppose if I go to a shop and you try to buy a mouse, right? They'll tell you what the current price is. With mouse is very difficult because the MRP and everything will not change much. But this happens with, let's say, real world stuff like say petrol, right? Fuel. So if you want to refuel your vehicle, if you have your vehicle, I mean, if you're going to be driving, let's say car or any other motorized two-wheelers, right? Today you might use electric vehicle when you become bigger, when you become older, but then today we still use these fuel-driven engines, right? So if you are having a normal motorcycle and you want to fill up petrol or diesel on it, mostly petrol, what price will you pay petrol for? Whatever the current price is, right? That price for that fuel is technically a class attribute. In the entire city, in the entire town, or maybe in the entire state, a price is fixed by the government. The government says today the price of petrol is this. Tomorrow they'll increase the price a bit. Tomorrow later on they'll reduce a bit. Existing fuel, the price will change, right? That's a class attribute. No matter whichever station you go, same price you'll get. If you're buying gold, the price of gold is a class attribute. Just because you're buying gold from one particular merchant, he's not going to sell it to a lower price. He will lose profit. So if they say the price of gold is today, it's like 6,000 rupees or 5,000 rupees in India, whatever the price. I'm not even sure what the price is. It's always going higher, that much I know. But then that price is set as a class attribute. So whoever is selling gold in a given place will sell at that price. So class attributes are common to all the instances, all the objects, right? Every object will share it, right? This digits, right? I made as a class attribute. So if I define any variable inside a class directly and initialize it with a value, this becomes what we call as a class attribute. If at all I want to initialize some pins, so if I have two different 7-segment displays, the pin connection will vary. So if I'm even in this Raspberry Pi or here, Raspberry Pi Pico, if I put one more 7-segment display here, I've already wired some pins. I had used other pins, right? Other pins which are there here. The pins are different. So I say for the first display, this is the pin configuration. For second display, the other pin configuration. So the pins are instance attributes. So instance attributes you initialize inside the init method using a special technique like this.
Sir, do you save the 7-segment displayed underscore OO in the Raspberry Pi Pico?
Yes, yes. I'm writing everything in Raspberry Pi Pico.
Okay. Okay. Because I saved it in my.
Yeah, if you can also save it in your computer and later on you can upload it to yourself, Raspberry Pi Pico and run it. You can also do that. No problem. Okay, that also is possible. So here I'm just going to copy this pins in here and I'm going to make it different. Pins, when I say it's a variable, there's a difference between a variable and an attribute in Python. This is a Python language specific nuance. It's a language specific feature. Variables are just names. But when you say attribute, it is something dot name. What is that something? I should say this particular displays pins must be this configuration. How do you do that? You use it as self dot. Self indicates the current object. In this object, the pin configuration is this. So each object will have its own set of pin configuration this way, right? As a self dot pins is equal to, this is a comprehension which I used last class. You're instantiating multiple pin objects, configuring them as output pin. For each pin from this pin config must be all small letters this time because you're taking it as a constructor parameter now.
Sir.
Yes, Yuvans.
Sir, why did we take digits as a class attribute? Because it will remain same for all the objects, right?
Yes, that's why. That's why it's a class attribute. It's
But
gonna
like,
be-
how is it related to the object then?
it's related to 7-segment display. All 7-segment display objects will have this kind of a digit layout. Am I correct? I cannot use these digits in anywhere else. Only for 7-segment display it is meaningful. Outside 7-segment display, the digits is meaningless. Am I correct?
Yeah.
So it's like this. If I say the price of gold is today 7,000 rupees, if you go and buy silver, it will not be 7,000, be something else. Gold is that price of gold is class attribute for gold. Price of silver is class attribute for silver, right? So that's a class attribute. So class attribute is common to all the instances that belong to that class. They're shared by the objects of the class. There's digits, right? How to display on 7-segment display, no matter what display you have, it'll be the same. Because as long as the 7-segment display looks like this, looks like this one, right? Looks like this. It'll look similar. Assuming that you call the A, B, C, D, E, F in that right order, like I showed you in that diagram, it'll remain the same. Tomorrow you switch to a common anode display rather than common cathode. Even then, this will be the same. So it's a common class attribute. Okay, that's what it is. However, the pin connections will vary. So if I have two 7-segment displays on the same board, what pins I'm using for the first display connected to Raspberry Pi will be different than what pins I'm going to be using for second display. That is why I made this as a instance attribute. All instance attributes must be initialized as self.name inside the method. So you have a method called init, which takes self as an argument. The self is what? The current instance, whichever the object is there, right? The 7-segment display object, that is called self. It's like, you're asking 7-segment display, what are your pinouts? You say, my pinouts are this. That self is myself, right? So it's trying to say myself pins is equal to, this is the pin configuration, which I'm taking from the constructor parameter via pin config and working it accordingly. Let the print function be there. We'll remove it at the end. Now the show function is where we actually display things. And what we do here, this is where I'm going to copy whatever I did in the display function. This display function, I'm taking this, right? I need to change the variable names accordingly. So I'm going to use a proper variable naming this time. I should say, rather than calling it digit, I'm going to call it segments. Which segments to display, right? I'll call it as segments. Is equal to, I can't say digits because class attributes, you must always use class name, or you can also use instance name. Self dot digits of digit. Sorry. And now I write a for loop where I can say for pin comma segment in zip of, where do I get pins here? Okay, self dot pins. self.pins digit. Is a digit, it's called segments. Segments, pin.value of segment. Okay. Done. So basically it'll display this. Now let's try to run this now. Oh, there's some invalid syntax somewhere. I think line number 20 looks like some indentation error, or no, it's not indentation error, syntax error, right? Line number 20. Let me just check what the error is. Pin of p pin.out. Okay, I don't need this parenthesis. I added a parenthesis here. Not required. Oh, still it says invalid segment, line number 27. Okay, let's check what's the error. For pin, comma, segment in.
So you forgot indentation for pins.
Yes, this must be indented. Good. Yeah. So let's now try running it. But again, that's should have shown an indentation error. Surprised to see it shows syntax error. Okay, let's anyway check it out. Oh, pin is not defined. Oh, obviously. See here, I've created a class. So I'm using this class called pin, right? Where does it come? Machine, right? I have to load this library here. So to say, I can put this import inside the init method also. That is what I will do. But some people say put it on top. It's up to you. Because I'm using pin here, I can directly say from machine import pin. See this class, I'm only using in here, inside init method. Here I'm not using in show. In show, I'm getting the instance of pin and using it. So because I'm using it only inside the scope in this particular place, I'm just importing it. It's called as a local import. Importing it for local usage. Okay. So I'll run it now. Yeah, it worked way too fast. I will just switch my camera and I'll show you. I need to make some adjustments. First, I'll switch my camera. Just one moment. The last digit that got displayed is shown here. But anyways, what I'll do now, I'm just going to make some changes in here. I'll also use from time import sleep underscore ms, sleep milliseconds. And then here after digit.show, I'm going to use a sleep underscore ms of 2000, 2-second delay. So each digit will be displayed for 2 seconds, right? So now if you try to run this now, just see what happens. You can see how the digits are changing, right? You can see that over here. That's it. It finished, right? Once it's finished, right, you want to clear it off. Once I'm done with it, I should be able to clear the display. See, this display should not be left like this, right? It's not good. Once I'm done with it, I want to clear the display. So to clear a display, what I'll do is now I'll add another addition. What I want to do finally is I want to say digit.clear. Digit.clear. So I want to implement that clear method. So how do I do now? What do I do for implementing clear method here? All I need to do is this place, I'll implement clear of self. Clear takes no arguments. Clear takes no arguments because I'm calling this digit.clear and not passing anything. So what clear will do, it's a hack. You can see that. Look at the last digit we created. That's actually the 11th digit, which is all zeros, right? All zeros. So all we can do is we can ask it to show that 11th digit. And to do that, I think we can, we can just say self dot show off. We can just use maybe, it's 10, right? Index 10. 9, 10, I think it's 11, index 11. Actually, it's not 11 digits, it's 12th digit. You count it, right? So we'll try to do this. Now let's try running it. You can see that the numbers are flipping every 2 seconds. Ultimately, okay, turn on the video, Shivansh. All right, nice.
I know actually it's a like very complex circuit because of the number of wires.
Yeah, obviously the
So I
circuit
just
is
run the code and the 0 is
starts
shown.
at 0. Okay, turn on. Okay, very good.
I turn off. Turn on again. Turn off.
That's nice.
It's coming properly, right? Or is it
Fantastic,
mirror?
fantastic. Very good, very good. You should reset to 0 after this, right? Okay, very
Yes,
good,
sir.
very fantastic.